Hello students, the topic for today is entropy change in a reversible process. So consider a reversible process in which system and surroundings they exchange heat reversibly at a temperature T1, that is under isothermal conditions. So in such a case, the entropy of the system will always be equal to the entropy change of the surroundings, but with a negative sign. Now, by definition of entropy, entropy change is written as Q reversible by T. As we can always say, the entropy change is the amount of heat absorbed at the given temperature. Similarly, in case of surroundings, entropy change can be written as minus Q reversible by T because of the relation stated above. So, total entropy change is basically the sum of both changes, that is delta S system plus delta S of surroundings. This will give you Q reversible by T plus minus Q reversible by T, which will be equal to 0. That means in a reversible process, total entropy change is always equal to 0 because amount of entropy increased in the system is offset by the similar entropy change in the surroundings. Therefore, there is no entropy change in a reversible process which is occurring at isothermal conditions. Now, moving on to the entropy change in an irreversible process. First of all, note that if an step of reversible process is irreversible, then whole process becomes irreversible. It is true in case of any cyclic process. So, starting here, entropy change of the system is given by Q reversible by T by the definition of entropy. Similarly, for the surroundings, now there is a change. We will write Q irreversible by T because now one step of the process is irreversible, and we are considering that in case of surroundings the heat exchange is irreversible. So, we can say that this is again by definition. Now, total entropy change is delta S system plus delta S surroundings, that is equal to Q reversible by T minus Q irreversible by T. Mark it as equation number 3. From here on, we will use that work done in a reversible process is always maximum as compared to any irreversible process, that is work done for reversible is greater than work done in case of any irreversible process. Now, using the first law of thermodynamics, we can write that for any reversible process, delta U is equal to Q reversible minus work reversible, and similarly in case of any irreversible process we can write Q irreversible minus work in case of irreversible process. Now, as we know that internal energy in both cases is a state function. So, its value will not change until or unless the state of the system changes. Therefore, from equation 4 and 5, we can compare that Q irreversible minus W irreversible becomes equal to Q irreversible and work done in case of irreversible process, and from equation 3 we know that work done in case of reversible process is always higher than irreversible. Therefore, since work reversible is greater than work irreversible, this implies heat exchange in Q reversible process must be greater than that of irreversible. Now, dividing both sides by T, you will get Q reversible by T is greater than Q irreversible by T. That is, by definition, entropy in case of system is greater than entropy change in case of surroundings. This comes from equation 1 and 2, or we can write delta S of system plus delta S of surroundings is always greater than 0 when the process is irreversible, that is delta S is always greater than 0 or positive for irreversible process. From this equation number 6, we can say that any spontaneous process proceeds with a net increase in entropy. That is, whenever the process is spontaneous, the entropy is bound to increase. Therefore, what we have studied in current video, that in case of reversible process the entropy change is going to be 0, but in case of irreversible process the entropy change is always positive for a spontaneous process, and that entropy change includes the entropy change in system as well as entropy change in surroundings.